So we've thought about the electric field inside a conductor. It's always 0. Now let's look at the electric field outside of a conductor. All right, so let's draw just some surface of a conductor, some lumpy thing. The details of the surface don't matter right now. And although we usually use metals for conductors, let's imagine the free charges here are positive, just to make the drawings nicer. And let's have it be charged. Okay, so say this conductor has some charge on it. We know that the charge will move until the E field inside is 0. That's what we covered before. Because it'll move to make the field 0, because if the field weren't 0, it would keep going. Right? So the charges will move until the field is 0. So they'll collect somehow on the surface of this conductor. And they'll arrange themselves in a way to make the inside 0. Maybe it's because the conductor is charged. Maybe it's because it's been put inside an electric field. Doesn't matter. The point is they will arrange themselves in an electrostatic equilibrium. E field inside will be 0. So let's think about now the E field outside. So anywhere you go, the E field just outside could exist. And in a Cartesian coordinate system, it could have 3 components, x, y, and z. Let's do this in 2D since we're writing on the board and say, well, it could be in any direction. And in that direction, you could build it up into an E field that is perpendicular to the surface and an E field that is parallel to the surface. Could happen. So I don't mean inside. Inside it's 0. What is the field just outside? That's the question, right at the interface. So this is possible. Any field that exists right outside could be broken into those 2 components. So we just have to think about which of those components can exist. Okay? So the E field just outside actually can exist in this direction, perpendicular. Because you would say, well, whenever there's an E field inside, it goes away because the charges can move in a way that will cancel it. Well, this is the one way they can't move. They can't move out of the material. They're stuck in the material. So E perpendicular does not equal 0 because the charges can't move outside the conductor. Because to move outside the conductor, they have to move perpendicular to the surface. Now, let's think, can there be a lateral field? Well, in this case, there can't. If there were a field vector that built up that way due to this charge, what would happen? Well, this positive would be pushed that way a little bit. It would leave it a little bit negative there. It would make a field that would cancel that field. And if it wasn't enough to cancel it, it would do it a little bit more. It would do it until this field is driven to 0. 3 charges, and then that's enough to kill it. Okay? So for a field that's parallel going along the surface, E parallel, it does equal 0. Because in that direction, along the surface, the charge can move. Okay. So it's the same argument, the same idea for why the field is 0 inside. Also occurs for the field just outside. It's just what you'll end up with is only the perpendicular field can exist. So if you look at the field of this charged conductor, in this case, the field lines will all be perpendicular. Here it's kind of going off that way. Here it'd go off that way. So it's easy to draw the field around a charged conductor. You just draw the lines perpendicular to the surface everywhere. Or even if it weren't charged, even if you had some negative charge out here, and these field lines were just between the metal and the negative charge, they would still also, they always terminate perpendicular to the surface of the metal. Okay? So E field is always perpendicular to a metal surface.